we are still in chapter 4, which is building good data set and data processing. And we'll try to finish it today, and maybe tomorrow we continue with the next chapter, chapter 5, compressing data via dimensionality reduction. So what we have been doing, you can see like in chapter 2, we train a machine learning algorithm for classification, and now chapter 3, we take a tower of machine learning scikit-learn algorithm, right? We take a tower of that. And now chapter 4 is basically before you train any machine learning algorithm, is actually good to create a good training data sets, like, because any machine learning algorithm that does a good thing, one of the things that involves for giving a good prediction is having a good quality training data set. So that is what this chapter is all about, that we have been discussing. And we discussed, for example, one of the issues that we may see in our data set is like it has some kind of missing data, which makes our data not quite good, right? So we discuss about this stuff in chapter 4, and I believe you read. So you can see we discuss of missing data. So if your data set has some missing value, you may not actually get a good performance. So some of the things we can do with missing value is to maybe in some ways to remove the missing value. Maybe you can do imputing missing value that we discussed. Like you can take maybe the mean or propagate. And now we discuss about handling categorical data, which is basically if we look at this chapter 4, we talk about handling categorical data, where we discuss about using how we can change this to numerical, how we have nominal features and ordinals, where we can use one-hot encoding. We discussed that. But today, what we be Hello, can you hear me? Hello?
Yes, you don't. You don't. You don't.
Okay. So kuna jina? Can you hear? Okay. Can you hear me now?
Ana jinka.
Okay.
Yana ɗaukewa ne yana kawo.
Yeah, so energy yana da issue. Abin da yake da shi yana da issue. So yeah, so what we discuss also handling categorical data. If our data set, as we saw, is some ways like categorical, machine learning algorithm don't actually works well with categorical data. We discussed that we need to convert this category to numerical. So where we discuss about using what is called level encoding and one-hot encoding, right? Which is basically this. One-hot, if we have categorical data, we need to do this, and we discuss this in scikit-learn. We also discuss the next thing. I think we also discuss partitioning our data set. So one good thing if you want to train machine learning models is we need to divide our data set into train and test, so it is also a good way to preparing the data set. But how can you prepare your train sets and test set? It depends on the amount of the data set you have, the size you have. So, but one good, commonly used split practice, we know, is you can use 60-40, 70-30, 80-20, depending on the size of the data set, right? But if you have like large number of data set, even 9:10 is quite okay for you to train your model. So it depends on the size of the data set. So that's what we discussed. And today we're going to discuss bringing features on the same scales. All right, we discussed this one where we said, okay, when you have many features and they are of different scales, we need to put all these features into a single scale. We discuss about normalization, where we talk about this is how you do minimalization using min-max. We also discuss about the standardization, which is it. So, and yeah. So today what we'll discuss is what is called selecting meaningful features. So what is the meaning of selecting meaningful features? So for example, you can see here, I have 1, 2, 3, 4, 5, right? I have 5 features. Now, having these 5 features, are they all important for us to train machine learning models? Some features are not quite important, right? So we need to like select those features that are really important that can make good predictions. So that's what we continue discussion today. So any question today before the next? Any question? Okay. Hello, can you hear me?
Yes.
Okay. So the selecting meaningful future. So we are still talking about this chapter. What is the title of the chapter? Making good data set. So what is the making? So for example, you have your training data, which is containing, for example, you have like 20 features, right? So when you have 20 features, when you have 20 features, are you going to train the machine learning model with all these features, or you need to select something, right? So that's it. So there are many ways for us to select useful features. One is we have what is called, okay, so here we can see not all features are equally important from machine learning perspective. We can actually do what is called overfitting. What does that mean? If a model perform much better on training data set than the tested, this observation is strong indicator of overfitting. So example here, we have a training set. We have this is the training set, and also this is the test set. And now you train your model and you find out the model performs better on the training set, but it does not generalize, right? Now, this is called overfitting. Now, how can we avoid this overfitting? There are many ways for us to avoid this overfitting issue. One way is to actually collect more data. So it means when you train this model, but it does not generalize on test set, it means you have few data set on your training data. So to solve this issue, you can collect more training data. Now you can solve the issue of overfitting. Another way, but it's also difficult, we can use what we call regularization. We can introduce something called regularization to prevent overfitting. We can choose a simpler model with fewer parameters. We can reduce dimensionality of the data. Regularization is a method that we can use that can zero out, we will see soon. So if we do regularization, for example, now if I have 1, 2, 3, 4, 5 features, regularization will reduce the features maybe to 3. We only have 1, 2, 3, as we see an example via what we call dimensionality reduction. You can introduce you choose a simpler model. So when you do like train a model and now the model overfit, it means your model is complex. So you can change a simpler model. For example, you use deep learning model and it works. It's complex model. So you can select maybe less some stuff, or you can do this. So we're gonna see these ones and see how can we prevent the issue of overfitting. Now, the first one, collecting more training data. Now, assume you train data, you get some data from GitHub, somebody, and you train your model and model is overfitting. You are not even the first person to create the data set, talk less of getting more data. So getting more data is not always feasible, right? Because you may not have the luxury of annotating or getting much data. In some situations, the data is not even available. So if solving the issue of overfitting using collecting more training data can do, but collecting more training data is not feasible. Yeah, so the next one is using what is called regularization. Any question regarding to solving overfitting problem with collecting more training data? Anyone with question or anyone want to add something? Okay, now let's look at regularization. So what is the meaning of regularization? So in machine learning functions context, what we mean by regularization is we try to minimize the we try to minimize the optimization function, which is our objective function. We try to minimize it. And there are a lot of theoretical concepts they discuss in the book, but I just ignore the theoretical part because we're gonna just see the practical part. So you can read the regularization theory from the book, but what does that mean to introduce penalty? Now, some models, they have what is called regularization parameter, which is a penalty. For example, we have what we call L1 and L2. I think here, do I mention? Okay, we have what are called L1 and L2 regularization as penalty against model complexity. Can you see what we mean? When we say model complexity, meaning model that is complex, is, you know, is having many parameters, is complex. A less complex model is simpler model. So you can see here we say choose a simpler model. So if you train a machine learning model with a particular algorithm, and that algorithm is complex model, it will overfit the training data. So to solve this, you can use a simpler model. But how can we use regularization? So we can use what are called L1 and L2 regularization as penalty against model complexity. Meaning, if your model is complex, if you have a model which is complex, because the model can do a good job. So you say, okay, this is a model, and I want to use this model to train my machine learning model. But how can I prevent overfitting? One good thing is to use what we call L2 and L1 regularization. So they regularize the model. They introduce some kind of bias so that the model will not overfit. Now, how can you do that? It's very simple in scikit-learn. You can see here we import from logistic regression. Logistic regression, we call the model. Now you can see something called error penalty L1. That is L1. And now here you can see we have some of our parameters. We have, this is a solver, which is meaning the algorithm that we will use, and we want to use multi-class. And now this is penalty. So if we do this, now this is our regularization parameter L1. So what regularization in fact is doing, let me show you what regularization is doing. We already know that this is how we are doing if we are training a machine learning model. Like, this is our weight, this is our future, weight, future, and this is bias. I believe you don't forget this. This is our weight, this is a future. When we are training a model, we are always trying to find this weight, because this future is what the model comes with. This is future is this x, 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 x. Now, what we are trying to find is, we are trying to find, for example, these weights so that we can fit the model and make predictions. So these are what we are trying to find, always weight and bias. Now, if we train logistic regression here, we can be able to see what are these weight and bias, So we can call our model LR, logistic regression here, that we can use the logistic regression that we fit in here. We fit our, you can see we train the model, logistic regression, we fit it here. Now, since we fit our logistic regression here, we can call the intercept. So you can see these are the intercept, because here we have many intercept. You can see this is the intercept, intercept underscore here. And this is the coefficient, logistic regression and the coefficient. So these are weights. Can you see the weight? Because we have many weights. Look at the weights, right? Now, what regularization is doing. So regularization is, if you introduce regularization, because here we introduce regularization, what it's doing is that it zero some of the weights. So if, for example, this weight is 0, you mean if this is weight is 0, it means this future will be eliminated. So it means if I have here like 1, 2, 3, 4, 5 future, Now, if I make this weight is 0, now this feature is eliminated. So if I have x1 up to x5, if I 0, 1, 2 weight, it means I'm going to use only 3 features. So this is what regularization is doing. So you can see here, some of the weights here are 0. Can you see weight is 0, 0? Can you see 0? Some of the weight are 0. So this is basically what regularization is doing. So because you can see here, if I sum every value here, x, w1 flex, x1, everything, this model may overfit in some ways. This model may overfit. Now, to reduce the overfitting is just to cut some part. So we can remove this part. We can remove some part and use only some part. So that is what this. So you can see L1 regularization can serve as a method for future selection. So you can see regularization serves as method of future selection, because when we zero this x1, we zero x2, we only use maybe 1, 2, 3 features. This is future selection, right? We only use 3 features. So you can see this one, we can say, we can think of, L1 can serve as a method for future selection. We just train a model that is robust to the function irrelevant features in this data set. So you can see L1 will zero the coefficient, the weight of irrelevant features. So maybe this feature, maybe feature 1, feature 2, does not have any relevance to the prediction of our target. So when we say use our regularization, maybe L1, what it will do is it will zero all the weight that when we multiply by x1 or we multiply by x2, they will be 0. So we will only use these 3 features. So that's what regularization does. It makes your model less complex so that it will not overfit. Yeah, if you want to make the model even more complex, you can increase the regularization parameter. So you can see here, we have many 0. So let me do this. You can see L1 is 0.1.0. So let me use maybe 0.001. Let's look at this. Okay. So let me show here. Look at this. Can you see what happens? It zero all the coefficient, right? And you can see because it zero all the the weight are all 0. Look at our training accuracy and test accuracy. Can you see it's 0.3? It's not a good prediction because the weight, we didn't find any good weight. So that is, what about if I put 0.01? Still this, what about 0.1? Okay, that's what we do. So you can see this. So when I run this coefficient, you can see some of the 0.00. Can you see this is 0.00? So this is what we mean by regularization. So to recap, what we are seeing is this last part of this chapter is when we train a machine learning model, it can overfit. But how can you reduce the overfitting of machine learning model? Overfitting is when you train a model on training data set, but it does not generalize on test set. What do I mean when I say it does not generalize? In machine learning terms, when you say generalization, it means you train your machine learning model on training set, it does a good thing, and now it does a good thing on test set. This means it generalized from training to test set. But if it does not generalize, it is doing overfitting. There are many ways to reduce overfitting. Number 1 is collect more training data. Number 2, introduce a penalty for complexity via regularization. That is, number 1 is collect more training data. But the problem is that we cannot actually get more training data because data is expensive. So if your model is overfitting, one way is to, if, for example, you have like 1,000 training data set, and you think that the model is overfitting, get another 1,000 so that you have 2,000 to train the model. But it's not always free. Get training data. So this is not feasible. The second one we are talking about is introduce penalty for complexity. So to introduce one parameter called regularization. This regularization, because the model is complex, that is why it learns everything at the training data, but it does not generalize. It does not do it. So we need to introduce penalty, meaning the model is complex. It learns everything in training data because it performs maybe 99 on training data, accuracy is 99. But on test set, it's maybe 50, so it's overfitting because it's doing good thing on train. So it means the model is very complex. It learns the training data all so that it can remember everything. Maybe the data is so small. Now, how can we penalize this model to make it less complex so that it will not remember everything in the training data? This is what we are talking about, regularization, by introducing a term called penalty. So how can we do this penalty? This penalty, we have what we call L1 and L2. As I said, there are theory behind that you can read in the book, but to introduce penalty, it's just this term. So you can see here we're going to use logistic regression. We're going to create logistic regression object. And now you can see penalty is L1. So this term, L1, will basically make our models. Oh, here I'm using something. Oh, sorry. So here it will make our model less complex. This parameter that I'm working on is not the regularization parameter. Sorry, I was taking something here. Our regularization parameter is, our penalty L1 is this one. So here, introducing L1 is regularization parameter. And we have also C, we have solver, we have multi-class. And now when we train our machine learning, here, this is what we have. So we can see here the model here on training set with 0.984 and on test set is 0.97. So you can see this model is doing good because 0.98 is not far from test accuracy. So our model is doing a good thing. That is basically about the approach. So I said, what does that mean by the regularization penalty? The penalty, if you remember, when training a machine learning model, we are always trying to find the weights and the bias, right? So that we can fit in. We find the perfect weights and bias so that when we train the model, we can predict good. Now, what basically the penalty is if our model is complex, it zero some of the weight. So for example, I have I have W1, X1 in the future up to maybe X12. So if you sum all this one from W1 times X1 plus W2 times X2 up to X1, X12, W12, X12 plus B, you sum them, that is why they are complex. So one way to do that is to maybe to cut some part, maybe W1, X1, W2, X2, W2, X3, to cut it and drop it and sum the others. But do we cut arbitrarily? No, we select features that are not important and make their weight 0 so that when we multiply by them, the weight is 0, everything is 0. So this is what it's doing. So you can see this, the coefficient here as we discussed. If you look at some of the coefficient here at 0, so it means the model, we met some of the coefficient here. So that's theoretically behind what this is doing. Any question before we move on? Okay. So let's look at how regularization impacted. So we can see here also we have the inverse, the C, which is inverse regularization strength. So you can see here you can see here that the strength of the our regularization here is that the lower the value is, so when we move lower here, you can see all the parameters will be zeroed here. So you can see this is coefficient of the weights, and this is our regularization C parameter. As I gave example here, the C parameter, for example, when I increase it to 0 to very low number, you can see the prediction is worse, 0.3. And when we look at our weights, what will happen? You can see all our weight becomes 0, right? So that is what we are showing here. You can see the more, because 10 power minus 5 is very slow, right? So the more our C regularization parameter, the more lower it is, all our weights will be 0. Can you see the line in 0? Even if we use 10 power minus 3, which is 0.003, all our weight will be 0. So what this is telling us is that the lower the weight are, the more regularized we are doing. But so we need to include take some maybe 10 power 1 maybe 10 power -1 or some very small number, right? So that's when our regularization will work. So any question before we continue? Okay, so now we have seen that regularization can now serve as future selection, because when we do regularization, we are zeroing some of our some futures and now selecting some, right? So let's move on to what is future selection. So when working with large data set, it can be time consuming and also even resource consuming. So for example, when you are working with large data set, for example, 1 billion or something like that, it is common to have large number of futures, right? So, but not all these features are important. So we need to weed out or remove these features and select the best important. That is what is feature selection. So there are many ways to do feature selection, right? One of them, as you can see here, filter method, Rafa method, embedded method, hybrid method, right? So different ways to do feature selection. What we can use now is that what we just use now, where we use feature selection here, where we use L1 regularization, because we select some features, which part does it belongs here? Who can tell us? Who can tell us, like feature selections, which class does it fit now? You can see here we have what is called embedded method, 3 regression coefficient, right? Regression coefficient, because you can see here, we are zeroing the coefficient, right? We are zeroing the coefficient. So this is one of the embedded method. So there are many ways to do that, and we'll see. These are some of the benefits of feature selection. It allows you to build your model easily. So if you have like 50 features and you select most important, maybe now you have 10 features, then you will build your model easily, right? And you can have model performance to be more accurate. Right. Okay. Okay. Any question? All right. Okay. I think this is what I have shown here before. Yeah, this is what I've just shown here, where we do introduce our L1 regularization, right? We train a model here, and now here, and you can see here the parameter here, we use 0.6, and now here we just want to plot what we want to plot the futures in the data set we have. So this is a data set we have, which is for the what is it called? The data set for wine data set, if you remember them. So you can see here, these are some of the features: alcohol, metallic, ash, alkalinity. These are some of the features based on their importance. So this is it. Okay, so that is feature selection using regularization. So we now know that, yes, if you have a model that is overfitting the data, you can do many things. One of the things we just mentioned is that you can collect more training data to reduce the overfitting, or you can introduce penalty. Now, does every algorithm has this regularization parameter? Does every algorithm has this regularization parameter? So if you look at this here, we can see that logistic regression has regularization parameter. Can you see penalty? Can you see penalty? It means logistic regression has penalty parameter, which is L1 or L2. Now, if you come here, you can see what is a penalty, L1, L2. You can see there is another one, elastic net. I don't know them. But, by default, it's L2. Now, but some algorithm doesn't have this regularization parameter. So let's look at another method for for selection features. So sequential feature selection algorithm. So an alternative way to reduce complexity of the model and avoid overfitting is dimensionality reduction via feature selection, which is especially useful for unregularized models. So it means we have some models that they don't have regularization parameter like L1 or L2. Now, if your models, it does not have this L1 or L2 regularization parameter, we can use what you call we can use what you call dimensionality reduction also via feature selection. So what is feature selection? So as I've just shown you, there are two things that may be confusing in some way. We have what is called feature selection and feature extraction. So feature selection is when you have features, you select the most important one. But we have what is called feature extraction. So feature extraction is like you create features from existing features. Let me give you an example. You want to create predict maybe whether somebody is going to graduate with first class or not, right? First class or not. Now you have all his grade in level 1. 1301, he has 0.1, something like that, you know. In level 2, you have all his grade. So you arrange them in as columns, right? But using all these, his grade in 1301 in level 1, for example, here, CSC 1301, he has, for example, 70, right? And maybe another CSC 1130, he has maybe 22, 34. Now, maybe let's assume this is year 1. And if it is year 1, maybe we can say, okay, we can have his GPA, right? His GPA. So this GPA will be somehow also a feature, right? So this GPA, we know GPA is calculated based on existing courses, right? What he has here and here, y divided. So you can see this feature is now extracted from this existing two features. And GPA will be a good feature to determine if somebody is going to graduate with first class or not, right? So this is called feature extraction. We derive information from the feature set to construct a new feature. So if you have grade of student only, now it's, oh, I need to create maybe GPA for that student. Now for GPA, you create, for each year, you create GPA and add it into the data set. So now this column for GPA is called feature extraction. I don't know if that is any question regarding what is feature selection or extraction. Right. So that is that for feature selection. So this algorithm is also another way to do to reduce the complexity of your machine learning algorithm using feature selection, as we have just seen using L1. So L1 regularization also, what it does is select some features, right? So this algorithm also, sequential feature algorithm, selects some features. So if you read more about this, sequential feature selection algorithm are a family of greedy search algorithms. So there are many, meaning there are family of algorithms that are used to reduce the initial dimension features space to k-dimensional feature. So you can see it's just like when I've just explained here, if I have a data set here, I have 1, 2, 3, 4, 5 features of my data set. Now it reduced from D features, maybe from 5 features to 3 features. Maybe it will drop some 2 features, but it doesn't drop just arbitrarily. It will try to find which feature is less important, which feature is more important, and select those that are more important or discard those that are not important. So this algorithm also did something as we saw in L1 regularization. So it's called sequential selection algorithm. Yeah, so that is this algorithm, and there are many. So here they basically try to implement the algorithm, but it's also implemented in scikit-learn. So they say they make here that let's practice our coding skills to implement the algorithm. So here they implement the algorithm. We don't need to go over through it, but we can just use it. So what is the name of the algorithm here that is implemented? You can see class SBSS, sequential, what does that mean? Sequential broadcast or whatsoever algorithm. Okay, So they just call the algorithm called SBS, right? Which is the algorithm. So it's implemented here, which is the same as, if you remember our first classes where we implement algorithm from scratch, so that we get the intuition how it is done, right? So this is also the implementing it. So now let's do it to do feature selection. So you can see here we use k-nearest neighbor. So k-nearest neighbor, we will use it to do that. So k-nearest neighbor, when we look at k-nearest neighbor, look at it. Does k-nearest neighbor has penalty parameter? Can somebody tell us? Can we use regularization in k-nearest neighbor algorithm?
No.
It doesn't have.
Hello?
It doesn't have the generalization, regularization attribute.
Can we use regularization parameter in k-nearest neighbor algorithm?
We can't.
If you look at this, as I said, some algorithm we can use regularizations, while some algorithm you cannot do regularization. So for example, when I say logistic regression, look at the signature here. You can see we have penalty parameter, which is L1 or L2, that allow us to reduce the complexity of the algorithm. Meaning logistic regression, from here I can know that, hey, I can use penalty, I can use L1 or L2. For me, I don't even remember, but from here you can know, does this algorithm have? So because here you can see, when I just put here, I can see penalty, it means it has L1 or L2. But k-nearest neighbor, you can see here, if you want to use k-nearest neighbor algorithm and your algorithm is overfitting, the question is, can we use L1? Can we use regularization L1 parameter to do to regularize the model to make it's not overfitting? No, because
we cannot, because it doesn't have the
here, k-nearest neighbor does not have penalty parameters. Can you see that? So you cannot use L1 or L2 in k-nearest neighbor. In that case, you can use other ways to actually make the model does not overfit your training data set. So one way here we just said is using this an alternative approach, which is sequential feature selection algorithm. So this algorithm that we implemented. So here, how does the algorithm works? So here you can see we call the algorithm SBSS. And now, because we already create our object called KNN algorithm, we just call the KNN. And now we select K features. How many features do we want to select? Selecting the features. So you provide the number of features, because you can see here the algorithm that is implemented. We can see K features, the estimator. Estimator means the algorithm and the number of features that you want to select. And yeah, so you can see this is the algorithm. Now SBS, we create another object SBS, and now we fit it. And now since we fit it, we can basically do some kind of floating. So here, this is something that we can see here, which basically show us that the performance of our algorithm, for example, with few feature here, for example, one feature, can you see that the algorithm perform worst 0.85, but with 4 features, say number of feature 12, the algorithm does a good job. But when we increase the number of features, possibly the algorithm will not perform very well. Let me run it again. Okay, yeah. So any question? So this is something that has been implemented in the book, and we can. So the main idea is this. The takeaway in this is that some algorithm does not actually support using the L1 regularization. You can follow other ways to regularize the model. So yeah. Oh, okay. So there are many ways for feature selection in scikit-learn, and using this link, we can access them. Okay, any question? Then the last part is assessing the important features with random forest. Now, we have seen now we can use L1 regularization to zero out irrelevant features via logistic regression, and we can use SBS algorithm for feature selection to apply to KNN algorithm. So we can see these two approaches previously, but there is another useful approach for selecting relevant features from a data set using random forest. So in chapter 2, I think, or 3, we saw what is random forest, which is like ensemble techniques for putting many approach as forest. And what is this approach? So this random
Doctor,
forest
I have a
technique
question.
will show
something.
you what are the important features in your data set. Now, when you see the important features of the data set, you can select, if you have like 20 features, you can just run random forest algorithm and use what is called feature important, just to see what are some of the important features in your data set. So these important features are the one that will make your algorithm to make good prediction. So you just select the important features and discard other one. Now let's look at it. So you can see here we import random forest classifier, right? This is our data set, the levels, future levels of the data set, because the data from wine, if you look at, you can see this is the data set, right? So data from wine here, I can say columns means I'm assessing the column from 1 to last one. So here you can see, this is a class level. So I don't want to use this one, but I want to select from here. I want to select these names, this one. So this is, you can see I said column. I set the column here. These are the features: alcohol, malic acid, ash, alkalinity, magnesium, protophonum. These are features of the data set. So here, feature level, can you see that? So I want to find out which feature is most important in my data set. So if I find the top features, I can select only them and train my machine learning model, because it can perform better, and discard the rest. So this is the important, so how can you do that? So this random forest come with an attribute called feature importance. So this feature importance shows you which features are important. So now here you can see we want to create a random forest algorithm, right? Random forest classifier, number of estimators 500. We just create an algorithm called random forest, and now we can fit the algorithm. Can you see that we're given train and y train? And now we can use this forest, the object that we just trained, forest future importance. So you can see, remember, you can see there is underscore at the end, future importance. Can you see that? Forest future importance, and now assign it to an object, something called importance here, right? Now, if we look at this here, we can see. Yeah, so you can see here, it gives me future importance. These important features, these are the few important features. Can you see them? It gives me these features in, it gives me these features basically in what? In binary format, right? So what can we do to see these equivalent features in equivalent names, in these names? Because here it gives me some numbers, right? It doesn't make sense to me. How can I change them to be like it, arrange them in this? So you can see here I said agsort. So here agsort, what agsort is doing? Who can tell us? Who can tell us what is agsort? What is agsort? What agsort? So this is return the indices that will sort an array. So yeah, it's basically okay. Let me this. For example, I want to create so this is our array, right? Here we have an array 215, right? So if I call np.agsort, what is it guy doing on this one? So if I call this guy here, now who can tell me what is this doing? What is this doing?
What it does is it sorts the array behind the scene and return the index of each and every element.
What is the relationship between the result of AgSort and this array? Who can tell us?
Yes, the result is that one.
Okay, so we can see like the indices,
By Zoom.
if the indices that if they are sorted. So for example, what is the lowest value here if we sort them? So if we will sort these guys, this is how we will sort them, right? 1, 2, 5, right? 1, 2, 5. So it is giving me like, what is the, so here it means the indices of 0 when sorted is 0. Can you see that? Because Python start with 0. Can you see? The indices of 2 is what? 1. Can you see it? Give me 1. The indices of 5 is 2 because 0, 1, 2. So AgSort is a NumPy function that returns, just look at it here. AgSort return the indices that will sort an array. Indices that will sort an array. So what I want to do here is just like I sort the arrays. So okay, let me show you something like this. This is just Python. So you can see here np.agsort. This is the importance. Now here, okay, let me remove this guy. So look at, okay, right. Yes. Okay, yeah. Banaji in ana magana. So ba san me yake faruwa ba. Okay. So you guys, you are talking, it means I cannot hear you, right? Ah, okay. I'll find out what is happening actually, but I don't know what's happened. So if you can hear me, if you want to ask question, just write to me in the chat. Just write to me. So you can see here, if I have indices here, I AgSort. Here you can see I have 7, 2, 8, you know, it just returned the indices. But maybe I want to arrange them. So what this guy, remember here, I'm sorting this here in, I'm sorting this one. If I use this, who can tell us, who can write me, what is this guy doing? If we call this on this, what will this do? Who can tell us? Maybe in the chat.
We are reversing the order.
Yes?
We are reversing the order.
Yes, exactly. Oh, now I can hear you. I can hear you.
Okay, yes.
Okay, we are reversing the order. So you can see here, when we do this, we can reverse. So you can see the highest now. I mean, not highest, we are reversing the order, right? So what this means is that the future importance is like, if we do this, you can see we have this one, because it gives us the indices from the highest indices, but we want to sort them like so that we have the top futures first. So this is the one with top future. Yeah. So this is just a Python. So the main idea is this. What are we doing? Remember, what we are doing is we are doing what is called assessing future importance. Given us this machine learning data set with 10 futures or 20 futures, how can we determine which future is most important for our machine learning algorithm so that we can discard some futures? So this is what we are doing. We said we can use random forest algorithm. So this is, we use random forest, and now we create an algorithm. Now we we use our object prediction that we fit in, and now we call futures, and the futures give us this data set. Now we want to make meaningful of this one to show the futures, to show us the futures, meaning we want to convert it. So here, this is what I was saying. So we basically getting the index here, and now we can see here that I want to loop into the training data. So if I take this one, future excellent, look, let me show you this one, excellent. What is excellent? Chef 1. Yeah, so you can see here, what we are doing is we are trying to say how many sample futures do we have? We have 13 futures, right? We have from 1, 2, 3 up to 13. So shape 1, you can see here, this is basically training data shape. It is shape because when we say training data, the shape, what this gives us, it gives us the row how we have 133 row, right? And we have how many columns? 13 columns. So if we want to just see the columns of this, then we can put this one, right? It gives us this. So it gives us this. If we put 0, you can give us a row, right? So we want to loop inside the loop 13 times up to the number of features, and now just print them. So this is nothing but so you can see here we just print them future levels. So this is the future level. Remember, this is the future level. So when we show you this is the future levels, you can see them. We have alcoholic and stuff like that. So these future levels, we want to arrange them based on their importance. So this is what we are doing. So we can see that the indices, the first indices, future indices, this is the indices we have already. Can you see that indices? Can we see that? These are the indices. And now we basically index it. So, and now the indices are the important also, we index it. So this is basically showing us that now these are the most important. So provolone is the most important feature for your data set. Then this guy, then this, then this, then so these are the most important feature. So this is something very useful that you can even plot the important features. So you can see here, you can, oh, these are the important feature for your data set. So you can even plot them and see. So this is basically well, the end of this chapter. So we basically understand that the chapter is talking about is basically how can you make a good training data set, right? So you can see the data is building good training data set and data pre-processing, right? So how can you build a good data, good training data set? And we have seen that a lot of things, for example, how we can deal with missing value, how we can handle categorical data, how we can use select meaningful features. So for us to select meaningful feature, we saw that we can use L1 or L2. We can basically use a sequential. And now lastly, we see that we can use feature selection in random forest, which we show here to show us what are the important features. So for example, here, if I want to train machine learning model, I can just select maybe a handful, maybe the 9 and just discard these features, because you can see that 0.8, especially the last one, 0.01, 0.0, you can see that. And now just select maybe, importantly, if you select maybe 1 to even 5, you select 1 to 5, you train your machine learning model, it can also work well. The thing is that it, and give you good performance. The thing is that it doesn't take much data, time again, and stuff like that. So this is what this means. So, what this is saying, using future importance here, using 3, is also the same as it has been shown using the other method, which is SBCS. So lastly, as far as interpretability is concerned, the random forest techniques come with a good gotcha that is worth mentioning. If 2 or more features are highly correlated, one feature may be ranked very highly, while information on another feature may not be fully captured. So what this means is that if we have 2 features that are highly correlated, meaning they provide the same information, right? They provide the same information, then one feature will only be shown, the other will not be shown. But of course, we don't even want to represent features that are highly correlated. If we want to train a machine learning model and we find that 2 features are highly correlated, they give us the same information, we drop one and use only one. So this is also one of techniques that we use, but this is something. So finally, the summary, this chapter look at useful technique to make sure that we handle missing data correctly. So we show how we can handle missing data. And also it shows us how we can handle categorical data by changing them using, we talk about ordinal and nominal value. And now we discuss about L1 regularization. And now finally, we talk about the sequential algorithm. And the next chapter will basically be talking about the dimensionality regression, compression via dimensionality regression. So compression, this means that, what this means is that if you want to, you have your training data, you want to reduce the dimension of the data, so we can use dimension. So we'll see this. Yeah, so that's what we have for today. Any questions? So we are still moving slowly, but I think it's good. We are getting the good thing is this, we are getting the nut and bolts to train our machine learning model, right? So we are getting little by little the important steps that we need to have our arsenals when we come to do a lot of other stuff. Yeah, so that's what we have for this session. Any question before we move on?
Doctor, na ɗan yi missing na ɗan tashi na ce kamar KNN.
Yes.
Da muka yi magana a bayan feature selection.
Yes.
Za mu iya tunda muna dealing ne da muna so mu samu nearest neighbor, ba za mu iya amfani da PCA ba?
Yes, so exactly. So that is the main point we want to show here. Because this book, we have not discussed everything. The idea I was talking about using KNN here is that, so what I was saying, okay, let's go here. Yeah, so what I was saying is trying to show that using k-nearest neighbor, we may not be able to use regularization parameter to do to regularize the model, right? Mm-hmm. But you can use because we have regularized model, we have unregularized model. Some model, yeah. So some model you can regularize them using regularization parameter. Some you cannot. So k-nearest neighbor you don't have such finality. Now, how can you basically reduce some features? So you can use for model selection. We have a ton of ways to do that. PCM is one of the ways, and that is what we'll discuss next week in chapter 5. Compression data via dimensionality reduction. I think PCM is one of them. Yeah, look at it, Kaganshi.
Oh yeah. Component and yeah.
So chapter 5 will talk to us for those stuff that we need a different approach. I mean, to do compress your data from large data to reduce it. So principal component analysis is one way to do that, and we'll see that next week. Oh, maybe, I don't know, is it next week? So tomorrow we may be able to cover maybe this section. I don't know, even this section. We'll see what will happen. Okay, any other questions? Sorry, so while I was asking questions, so people are attempting to talk Bana Jikmoko.
Yeah, ni ma na yi dan yi magana sosai kana disrupting kamar baka ji ba sosai ne. That is why I keep
to ai idan irin wannan sai ku yi magana sai falale ne mun chatting ya ce wai ba a ji na ina ba maybe ba na ji.
Yeah, exactly.
Yeah.
Doctor, how do I know the regularized algorithms as a beginner?
Yeah, wow. So this is good question, Noor. So yeah, so this is a good question. How can I know that a model is a regularized algorithm or not? So let me share my screen again, my browser, I mean. Okay, Sklearn. So if you algorithms, if you wanna use any algorithm, because we are using this, so for example, you can come. So for example, we have seen logistic regression, right? No, let me show you. So for example, here you can see we have linear models, right? And we have everything here. Now, for you to know whether you have your algorithm has such kind of regularization is or not, the best option is just go to algorithm, because you may not have you don't need to know the implementation details. What you can do is just go to this scikit-learn page. For example, for me now, if you have which is the same here that I'm using with scikit-learn, just try to look at the documentation. So you can see this is documentation for k-nearest neighbor, but this you are seeing is the same content that is available in scikit-learn. That is one advantage. So here, this English, everything here is from scikit-learn. So for you to know, as I have given an example, it just try to see what is the documentation for this algorithm, like the density regression. So if I open the documentation for that, I can see that it has penalty parameters. We can see we have on this. Can you see that? So from documentation, because this is some really theoretical background, one need to know which one has this, from theory, but for implementation, you don't need to do that. So you can know that easily. So if, for example, here I can come with KNN here. I can see if so in KNN, you can see here, these are parameters. You look at it in the parameters, there is no any regularization penalty parameter, right? There is no any. So you can know from the documentation, because you cannot know everything from your own head and have all this stuff on your head. So that is one thing. So if you come here, you can see here logistic regression. You can see it has penalty. Can you see logistic regression has penalty? So if you go back to another algorithm, maybe let me go back. Okay, let me go to classification. Let me okay, yeah. Yeah, so K nearest neighbor. So K nearest neighbor. I want to see the code in the implementation. Okay, let me see the. Oh, no. Where can I see the code implementation? Yes, okay, I want to see something like this. So you can see here for KNN, nearest neighbor, there is no parameter for penalty. Can you see that? There is nothing, something like that. So this means that it does not have regularization parameter. Let's look at another algorithm, maybe generalized linear regression.
Ridge regression.
Yeah, ridge in again, ridge regression. Let's look at it. Ridge. Yes. Ridge regression. So let's look at it. It does not have, I think, deprecated. Anyway, so ridge also does not have, I can see So to answer your question, Noor, so this is basically how you can know where your, but the easiest way, if you are using, for me, if you are using, if you want to use the algorithm, just try to just look at the documentation. Yeah, that is it. But we will see more ways, even if those algorithm does not have regularization parameter, you cannot regularize it. In the next chapter, that is chapter 5, we will explore many different approaches to do some kind of feature selection and stuff like that. Okay, I must say this, please, if you are attending this session, try to practice this stuff and ask questions in the Slack. That way you can improve your Python skills. You can only learn by doing. So yeah, if you are just following, you may not actually grab. Oh, am I sharing? Am I sharing my screen?
Yes.
What am I sharing?
Your browser.
Ah, okay. Ina ta bayani ai kuma wani abin na tafi ina sharing kuma. Okay, so you can see here now we more ahead we go this data, then learn best practices for model fine-tuning, combining different model with same ensemble, applying machine learning for sentiment analysis. Wow, this chapter is going to be good. So we're going to see sentiment analysis, different way to do that. Yeah, so this will be cool. Okay, predicting continuous target variable. So this is regression, this is classification, and working with all level data, which is clustering. So any question before we go? Right. So if you have any question, just leave that question in the Slack, and we will be able to answer. And we see tomorrow, inshallah. And as I have not yet put these the notebooks, I think today, inshallah, I'll upload the notebook and share it in the Slack. Okay. So without much further ado, I see you inshallah tomorrow. Bye bye for now. Ciao. Ciao.